So our next speaker is Carlo Beenakker from the Leiden University.
Okay. The idea is that I use the microphone, right? That's the plan. Okay. I will do that. I will do that. So I take courage in this conference, this school lists as topics a whole bunch of things, and then there's the final entry which says new materials. So no Majoranas, no topological insulators, no LAO-STO now, but the new material of 2015, and I think also certainly 2016, the Weyl Semimetal. I'll try to do justice to the fact that this is also some sort of a school, and since I have an hour, which is very long, I will give you an introduction to Weyl semimetals. I hope this will be useful for some of you. And by all means, interrupt me during, this thing is not very pleasant, but okay. Interrupt me during, while I'm speaking. There's no point in waiting with questions until the end. That's not fun. And this is work which we put on the archive just last month. It's my first Weyl semimetal paper, so I've become now, but I'm very, very enthusiastic about this, and it's pretty much what I hope to be doing this year. And perhaps I can make some of you enthusiastic as well. No need to make Adi Stern enthusiastic, he's already a fan. So this is work I did with Paul Bayreuther, Jimmy Hutasoit, and Jakob Torzitwo, and we're all in Leiden. So yes, it was the discovery of 2015, top 10 breakthrough of physics world, science highlight of the year, many, many news and views articles, a whole bunch, probably close to a dozen papers in Nature, Science, Physics, Physics World, Nature Physics, and these were experimental papers. So the breakthrough is not a theory breakthrough. I mean, these things have been floating in the literature for decades. The breakthrough was a sudden surge of experimental papers because finally it was discovered which materials would work and which materials would not work. And somehow the materials theorists said should work did not work. And this is really a triumph of, let's say, material science, figuring out what works and what does not work. Whole bunch of groups, and actually in this audience, it's a pleasure actually to acknowledge that the leaders are Chinese physicists. This is very, very much a Chinese topic, and not just because of the IOP in Beijing, which plays a very important role, but also pretty much all the papers have Chinese first authors. So this is where the future is heading, looking east. Yes, it's the last, in this trio of particles inspired by particle physics. It's the last one to be discovered. We had graphene, which gave us the Dirac fermions, relativistic, massless Dirac fermions. Let's say 2005. That was a Nobel Prize. And then there's the Majorana fermions, discovered. I think discovered in 2012. Perhaps there's still some ambiguity there, but it seems they have been observed in the laboratory. And now, 2015, the Weyl fermions. So it's the last kid of this trio. And perhaps probably you've read something about Weyl semimetals, and you might say, okay, why the hype? Before we called it Dirac, now we call it Weyl. Isn't this just, three-dimensional graphene? That's the idea, right? So graphene has this Dirac cone, that's 2D, and now we do it in 3D, so we get px, py, pz instead of px and py, but who cares? That was certainly my first reaction. I just dismissed them as, in fact, even the Dirac fermions in graphene were called Weyl fermions in some papers. So I thought, this is okay, it's three-dimensional, probably there are more materials where it might work, but who cares? And that really does not do justice to the topic. So indeed, the band structure, if you look at the band structure, it's even drawn in 2D, because somehow, I'm going to, it's very unpleasant to be able to have to walk with this thing in my hand. very tiring for an hour to keep this thing like this. If you want a video, anyway. Well, okay. I'm a guest here. I'll do as you tell me to do. Okay, I'll do this. Okay, so yes, even if you look at the dispersion relation, people still draw it in 2D, right? They draw it in 2D simply because it's very uncomfortable to draw four-dimensional band structure. So yes, it looks like graphene. It's poisonous to boot. At least graphene was, reasonably healthy, I think. I'm not an expert, but tantalum, arsenide doesn't look very healthy to me. Perhaps some of you will tell me, no, it's all okay. Don't worry. But it looks ugly. And this really does not do justice to the topic. And there's some very simple reasons for that. So this is the dispersion relation of graphene, px sigma y, px sigma x plus py sigma y. But we all know that somehow this is fragile. Graphene has no topological protection. You put it on a substrate and this Dirac cone will just split. And the way we typically model a substrate is by adding this term sigma z with mu some substrate potential, and this opens a gap. And that's true. And so graphene is actually a miracle that it works at all because there's no topological protection. Now, if you go to the 3D system, you add a pz sigma z, you say, who cares? But all of a sudden, this mu sigma z term becomes harmless. I mean, it's just a displacement of pz. So there's actually no way to open a gap. There's no way to open a gap in a 3D Dirac cone, 3D Weyl cone. There's no way to open a gap. And so that's why we call this material to have topological protection. And that's really the fundamental difference between 2D and 3D Dirac fermions. And that's why somehow we use different names for them. We call the massless 2D fermions, we call them Dirac, and the 3D, we call them Weyl. They're topologically protected. Well, there is a way, of course, to kill this topological protection, and that's the usual way. The cones always come in pairs. And if you bring two of them together, then they will merge and a gap will open. But if they're far apart, there's a good, you could do lots of stuff to it, add disorder, do all kinds of ugly things with the material, and the cones will not disappear. So that's the first key difference. There's topological protection. That's the phrase. And that's also why I dare to talk about it at this meeting, which is about topological materials. And then there is one other thing which is kind of fun, and that is that something which we know. I mean, the Weyl fermion for half a century, particle physicists thought that the neutrino was a Weyl fermion. We now know that it is not, because it has a mass, but at least for a long time it was thought that the neutrino was a Weyl fermion. And if it's a Weyl fermion, it comes in two-handedness, two chiralities, left-handed neutrinos, right-handed neutrinos. And the same thing here, of course, in the solid state. So these Weyl fermions, there are left-handed Weyl fermions and there are right-handed Weyl fermions. And I'll tell you more about that in a moment, but this is important to keep in mind. This is, of course, something which you cannot do in 2D. I mean, chirality means basically that something rotates like a screw. So if you move forwards, it rotates to the right, and if you move backwards, it rotates to the left. And of course, in a plane, I cannot do a screw motion in a plane, so there's nothing like this chirality or this handedness in 2D. So these are special properties of 2D, of 3D. Okay, so it's fun. How about topological insulators? They're 3D materials. They're topologically protected. Is this more fun or less fun than topological insulators? I would say it's more fun than topological insulators. No, and there's a reason for this. You see, with topological insulators, the problem actually with topological insulators is that they're not insulating. And they should be insulating, but they're not insulating, and this is miserable. And so all the experiments on 3D topological insulators aim to get rid of the bulk and only look at the surface, because only the surface is interesting for a topological insulator. The bulk is annoying. But here it's different. A Weyl semimetal has an interesting bulk because it has this topologically protected Weyl cone in the bulk. So it's okay that it's conducting in the bulk. That's interesting. And it also has an interesting surface. And this is something to which we already have heard about in Adi Stern's talk. So these two Weyl cones, they have states which connect them. They have states which go from one Weyl cone to the other Weyl cone, and these states live at the surface. And because they connect 2 points, they have a beginning and an end, and that's why they're not circles, as usually a Fermi contour is a circle or an ellipse in 2D. Right? We have a surface, so it will be a 2D contour. But it's not a circle, it has a beginning and an end, and so it's an arc. And that's why it's called Fermi arc. And an open contour, and that's really amazing, and that was discovered or noted in this paper from 2011, that Weyl semimetals would have on their surface this open contour. So that's fun. Also experimentally, you can do surface measurements, you can do bulk measurements, and both teach you different things, and there could be an interplay between surface and bulk. And again, we heard that in Adi Stern's talk, how surface and bulk have an interplay. So there's a certain phenomenological richness in this material which we do not have in topological insulators. I have no idea about technological applications, but certainly from the science point of view, Weyl semimetals have very, very much to offer, and that's why I'm pretty sure that this is where much of the field will be migrating to. Okay, some of the fun effects have been, have an ancient history, and it's just that nobody ever knew how to make these materials. And one of the most fun effects goes back to the 1980s. That's this classic paper by Nielsen and Ninomiya. And they noted something, and again, I'm repeating something which we heard from Adi Stern, that the zeroth Landau level in 3D has something which is really unusual. So in 2D, we know that 2D graphene has a zeroth Landau level, which is also unusual because it's at zero energy. Right? So in typical massive particles, the lowest Landau level has 0-point motion. So it's at n plus 1/2 h bar omega c. Remember the Landau levels? So the zeroth Landau level of massive particles has 0-point motion, but graphene has no 0-point motion. And there's this Berry phase which does that for you. And so the lowest Landau level in graphene is at zero energy. And that's interesting, but it's still a Landau level. It's at zero energy, but it's still a Landau level. Now here's something really unusual happens in 3D, because the zeroth Landau level in 3D can move along the Fermi surface, but it can only move along the magnetic field, but it can only move in one direction. And the first time you see this is really mind-boggling, right? So you have this cone, left movers and right movers, along the magnetic field, and I apply a magnetic field which is strong enough, and then there's one band which can only move parallel to the field, not anti-parallel. This is really bizarre, because if you look at this band, and this is the picture from Nielsen and Ninomiya, and they called this the Cairo Anomaly because they looked at just this one band, left-handed neutrinos, and said there are more right movers than left movers. Which, of course, is kind of bizarre, right? If you have a material with more right movers than left movers, there's no equilibrium possible. There'll always be a current flowing. And so this is somehow anomalous. Where does the current come from? Particle conservation, all kinds of bizarre things. And that's why it was called the anomaly, the Cairo Anomaly. Now, of course, in a condensed matter, we know it's somehow different. You can never have one isolated cone. There will always be the other cone. And so the right mover in this cone will be balanced by a left mover in the other cone. And there will always be some mechanism which equilibrates the cones. I mean, they're separated in Brillouin zone, but there will be scattering between them. And so we don't have to worry about current and equilibrium. There will be zero current and equilibrium, obviously, in condensed matter. So it's kind of unusual. And you can think now of all kinds of bizarre effects which may happen because of the fact that as long as you are within one cone, the particles only move in one direction. All kinds of bizarre effects. And that's basically what I'll be focusing on in this talk. And, well, this was an effect which was already somehow anticipated in the Nielsen and Ninomiya paper. They imagined creating some population imbalance between the cones. They introduced this notion, what they called chiral chemical potential. It's like a chemical potential difference in the Brillouin zone. So here's one Weyl cone, here's the other Weyl cone. And you somehow create a chemical potential difference or a population imbalance between the two cones. And then, then there will be more right movers than left movers, and so a current will start to flow, driven by this chiral chemical potential. And actually, to calculate this current, it's very simple. It has a universal form, and in fact, we can even do it right now. In fact, I will try to do it right now. To stay in the spirit of a school, if only there were, this is a blackboard, right? This is a whiteboard, yeah. I don't want to somehow damage this auditorium. No, it's not a whiteboard, are you kidding? This is a whiteboard, okay. So let's calculate it. So, this is like, ancient mesoscopic physics, right? We have a channel moves in one direction, and this channel carries a current I, this mode carries a current I, which is the chemical potential difference times E over H, right? Usually we say voltage, but then we say mu is E times V, and that's why we write E squared over H. Now I have chemical potential difference, so I could also speak of a chiral voltage, but okay, somehow the jargon is chemical potential. So E over H times mu, that's the current for one mode. But this Landau level, like all Landau levels, is massively degenerate. So there's not one, it's a bulk state, there's not one of them. There's a large number of them. How many Landau levels are there? Where the rule is the same, it's always in 2D and 3D, it's always the same number of flux quanta through the surface. That tells you how many Landau levels there are. So I have to multiply this by the surface. So say some width times some length. That's I'm thinking of some sort of cylinder or wire. So I look at the cross section. W times L times the magnetic field, and then divided by the flux quantum. That gives you the number of modes. So that's the current, which means that the current density, that's J over, right? That's the current density, is E over H squared times mu times B. Okay, it's not quantized. I mean, there's mu and there's B, but it has a universal coefficient. So if you would call this the response coefficient, then this is quantized, E over H squared. Amazingly beautiful result. Current density, which has this universal form, not the current itself that has the area, but the current density. Okay, let me not lose my thing. I think this is the one. Okay, this is all 1980s, and now that these materials are here, now we have the Weyl Semimetal. Say let's hunt for this effect. So you go to the lab and say, please apply chiral chemical potential difference, right? And it's one of these things which theorists invent, and perhaps there is a way optically. I mean, it's not impossible. There may be a way to apply a chiral chemical potential difference, but it's not something which we would know immediately how to do. And so this experiment has not been done. And there are other experiments which some are indirect experiments where you apply an electric field creates a population imbalance, and then you have a current. But of course, then you also have a current because you have an electric field. And so you have to somehow distinguish one effect from the other, and for that you need theory. So you need to do some transfer theory or whatever. So I really want to hunt for this pure effect. So the effect where the current is the pure thing and not some indirect effect of the Cairo anomaly. So this may work, but it's not obvious how to do that. So from now on, I will try to hunt for this effect in a different way without assuming that there's a chiral chemical potential difference. Let's see if that's possible. Yes, please.
Does this mu have some basic value, or?
Well, yes. So of course, in that context of this particle physics thing, this was just something which was invented. Now we have a real material, and then the mu is a material property. At least, okay. No, I should put it differently. I should put it differently. In this particular context, the mu is something which it's a population imbalance between the cones. So that is a non-equilibrium quantity. I don't know how to do that, but I know, for example, there's this material which is called molybdenum diselenide, where it has two valleys like graphene, and optically, using circularly polarized light, they can produce more electrons in one valley than in the other valley. And it may be possible, something like this is possible here, that there's some way to optically pump charge in one valley relative to the other valley. And then this mu would be something you could control externally. At present, this mu is I would regard this as not something which you cannot control. And so you could, of course, very well do this situation here where things are populated, say, to some level relative to the other cone, but then the other cone will equilibrate and will populate it at the same level. And so this is a fun thing to think about, let's say, in an academic setting, but it's not something you can easily implement. Now I want to show you, so let me already, this is one slide which anticipates what I'll be telling you, and then I'll give it some flesh. But this will be, let's say, the end of the school part, and then we'll go to the conference part. So this is a calculation of the spectrum of a cylinder with boundaries. So here, this was for an infinite system in a strong magnetic field. Infinite system, strong magnetic field. Now I go to a finite system in zero magnetic field. Finite system, zero magnetic field. Hey, what's this thing doing? Is Landau level? No, it's not Landau level. That's the Fermi arc. So that's this state which on the surface which connects the two Weyl cones. You see the left Weyl cone and the right Weyl cone. Left Weyl cone, right Weyl cone. I indicated mu here, but that's actually something different from this mu. This mu was meant to be some sort of population imbalance. This mu here is not a population imbalance. It's just that the left cone is higher, happens to be higher than the right cone. This is called inversion symmetry. If your crystal has inversion symmetry, that the two cones are at the same energy. If this crystal lacks inversion symmetry, then one cone is higher than the other. But of course, once you draw a Fermi level, you would draw a horizontal line. And so both cones would be populated up to the same energy. So there's no current flowing in equilibrium here, obviously. You draw a line, everything is populated up to the same level. No current can flow. Still, one cone is let's say, higher than the other, but they're populated up to the same level. There's also displacement, there's also displacement horizontally in K-space. That's time reversal symmetry breaking. So this is something to keep in mind. Weyl cones can be moved around in the Fermi surface. You can pull them apart. You can pull them apart in the momentum direction by time reversal symmetry, let's say magnetization. And you can pull them apart in energy by strain, by breaking inversion symmetry. These are the two handles which, and experimentalists are actually using these handles very, very effectively to pull the Weyl cones apart, either strain or magnetization. These are somehow given numbers. They're not controllable numbers, but you can play with your materials to get these numbers. So you see this state, which looks very much like this zeroth Landau level, but it's a surface state. And on the right side, I plotted this in real space. So in real space, it's this Fermi arc, which circles like this, but it spirals. It spirals upwards. And it has a velocity, and the velocity is the bulk Fermi velocity times this ratio of mu over beta. So it's some given number, and it spirals. That's really kind of amazing. I have the cylinder, wire, and the Fermi arc states not just move along the surface, but they spiral upwards. In one cone, they spiral upwards, in the other cone, they spiral downwards. Surface current. And now I have an immediate way to generate a population imbalance. So I have things which spiral upwards, I have things which spiral downwards. I want to create a population imbalance between the two to drive a current. How do you do that? Well, yes, please. It's completely unrelated. So Adi was working in strong magnetic field, and he was talking about bulk currents. Bulk currents land here. This is zero magnetic field. There are no chiral bulk currents. I would say that Adi's talk was more along these lines, with surfaces. Now I have zero magnetic field, no Landau levels, and still there is this thing which spirals, but it spirals only on the surface. And now comes the fun thing, because I know very well how to generate a population imbalance. I apply a magnetic field, a weak magnetic field, just a tiny magnetic field, couples to the magnetic moment. The thing has a huge magnetic moment, right? Because it circles and encloses a big area, a big area of the wire. And so, the ones which rotate clockwise will be pushed upwards by the magnetic field, weak magnetic field. The ones which rotate in the other direction will be pulled downwards. So you're creating electrons and holes at the Fermi level. Electrons move in one direction, holes move in the other direction, so you have a current. This is just the Cairo anomaly, but now for surface states, and driven not by this mu, which I don't know how to do, but driven by a weak magnetic field. So in a sense, it looks a very different effect, and in another sense, it's the same effect. And let's now try and give this some more flesh. Well, it will depend on the sign of mu and beta. So it will depend on how you... actually, in this picture, it took me a long time, but this is the correct orientation for these mu's and these betas. And you see it's mu over beta, so if I change the sign of mu, if I change the sign of beta, it moves in the other direction. So I think this is the proper way to think about it. And well, it is, okay, Fermi arc, it's a word. It's a word, and it happens if you look at Fermi surfaces. I'm not looking at a Fermi surface here. This is this momentum along this is a one-dimensional band structure. I'm thinking of a waveguide here. I mean, it's the same thing, but you don't see the arc thing here. Here I have a wire. Think of a waveguide. How do I look at waveguides? I say momentum is conserved along the waveguide. So that's this momentum here. That's the momentum along the waveguide. And then I plot the energy as a function of that momentum. And that's convenient because then if the slope of the energy tells you whether it's moving and in what direction it's moving. So this is not the way to draw arc states, because the arc state is if I ask, give me, for any momentum, whatever direction, give me points which are the same energy. Here, of course, there's just one point at each energy. Still, you see the arc because it connects one Weyl point to the other Weyl point, but it's not a Fermi arc because it's not at one energy. But that's just different ways of plotting states. There's nothing. Yes? Well, no. Yeah, then they will be on top of each other, and that then. Yes, they would cancel. Yes, they would cancel. No, so I really need to make this work. I need to break both symmetries, mu and beta, to break time Weyl symmetry and to break inversion symmetry, which is, as a theorist, the way we like to think of it, because then they're nicely far apart. Experimentally, this is actually still a problem. I mean, experiments typically break one or the other. One or the other. There's no fundamental reason why they can't break both, but some of the crystals which they're using at this moment either have strain or have magnetization, but not both. But here it's more convenient to break both. And I'm not sure what happens if you just break one of them. I would have to think about that. But I just made my life easy. Okay, there's this. It says the JDB is E over H squared. That's the same thing. We'll derive this in just a moment. So my claim at this moment that not only does this look like the chiral magnetic effect, it is the chiral magnetic effect. Exactly the same expression. But we'll get to that in just a minute. Yeah, I'm doing pretty well. Okay, so much for, let's say, the school part. Now a bit more the conference part. And, oh yeah, I called this Cairo Anomaly without Landau levels, but I'll come back to that title too. Now, some say that when the science part starts, you have to show a Hamiltonian. So I just flash the Hamiltonian, if you care. This is the Hamiltonian which we're studying. It's somehow modeled after some real system, but it's some sort of a toy model. It looks kind of miserable. Can't help it. Yeah, it looks much more miserable. But somehow, if you expand around the cones, then you see px sigma x plus py sigma y plus pz sigma z. But just if you want to do the full Brillouin zone, it has lots of terms. But you recognize there's a mu term, there's a beta term. Those are the two important terms. And so this is just a thing we put on a computer to actually calculate stuff. So all the plots I showed you, like this plot here and this plot here, are calculated for that Hamiltonian. There's no unique Hamiltonian. There's a whole bunch. It's topologically protected, so there's many, many Hamiltonians which will do the trick. This is just the one we use. Okay, now how am I going to calculate anything, right? So somehow, and Adi, you mean where you talked about being old and looking back, and actually, you didn't say, yeah, you said that. Yeah, you said at some moment. Okay. No, it was Professor Kapitulnik who talked about being old and looking back. Okay, so if Professor Joe Imrie would be sitting here, I would be even more comfortable, because then I'd say, remember, bring him my best regards if you see him. I would have hoped to see him here. Remember the 1980s. I remember the 1980s. 1980s, we were struggling with conductance and modes, and how did people calculate conductivity in those days? The Kubo formula. That was the method. And then there was this school which basically came from IBM, Rolf Landauer, Marcus Bütteker, Joe Imrie, who's the strongest of the three, right? He survived all three, right? And they said, no, you should think of this differently. You shouldn't do Kubo formula. You should work just at the Fermi level. There's transmission probability. You should think about injecting charge instead of driving charge by electric field. It looked kind of bizarre. What do you mean? Conductance is response to electric field. No. And so that was the Landauer formula. And I remember this very, very well. And it took like a couple of years before this was somehow accepted. And people said, yes, actually, if you have finite systems with boundaries, Landauer formula is much more effective than Kubo formula. It's the same, but it's much more effective. And here we're back in that time. So every single calculation of the chiral magnetic effect so far has been done using the Kubo formula. And we started out using the Kubo formula, and poor Paul Bayreuther spent nearly 2 years trying to do this with boundaries, and it just didn't work. No, not large enough systems, and incredibly painful. All these matrix elements, it was just miserable. And so we said, well, why not just, repeat the whole thing and write down a Landau formula? And it worked, and we got the same result, but we could do systems which were 2 orders of magnitude larger. And plus, we got a much better insight, because if you've looked at Kubo formula with these matrix elements, denominators, energy differences, it's miserable. And Landau formula you just see it happening in front of your eyes. So let's do a scattering theory for this. So here's, I just follow the usual recipe. For the scattering theory, I think of a waveguide geometry, I delete, and I look at modes, and I look at modes at the Fermi level. That's what you do. So here is this thing. This is like what I showed here, except that this is just for one kx. This is just one. I show one mode. Now I show all the modes, all the Fermi modes. You see these arcs. There are many of them. There's not just one of them. There's many of them. And you can see the Weyl cones. The Weyl cones are these bulky things at the left and at the right, and they're displaced. No magnetic field here. And the red dots, these are the modes at the Fermi level. I only drew the surface modes. You can recognize the surface modes because they are nicely dispersing. But of course also bulk modes. I didn't draw them. These would be red dots in this garbage stuff at the left and garbage stuff at the right. They're also there, and we have to take them into account. But in momentum space, you see a clear separation between bulk and surface. So that's convenient. That's one of the things which you see immediately in the Landau formulation, which you would not see in the Kubo formula. And, just repeat the usual argument. Okay, so we have current is E over H. There's transmission probability. In most of what I'm doing, I'll just put no disorder, so all transmission probabilities will be 1. That's easy. And then I have to know what's the non-equilibrium population of a mode. Now, in the Landau formulation, it's kind of easy. You say I have 2 reservoirs. I raise the chemical potential in one reservoir. So I only have to look at this one reservoir. So I only have right movers. And their non-equilibrium population is just mu, just or V, the voltage. But now it's different, because I don't have a population imbalance in real space. I have a population imbalance in momentum space. So both reservoirs will contribute. So I have left movers and right movers. And the population imbalance is because you apply this magnetic field, and the magnetic field either pushes them up or pulls them down, and so it creates electrons and holes. And so the population imbalance is given by the response. It's given by dE dB. Typically, you would have in the Landau formula, you have dE dV, which is just 1, right? If I apply a voltage, the energy goes up by EV. But now I have dE dB, which is something which I have to calculate. That's why it says here dE dB. I don't know what dE dB is. I have to calculate it. And then I have to worry about the sign, because in the Landau formula, I had only right movers. Now I have right movers and left movers, and so they contribute opposite to the current. So this number chi, which in the Landau formula is just 1, now has the EDB, which is something, and it has the sign. But apart from that, it's just, you recognize it just has the structure of the Landau formula. Okay, so this is how I want to calculate this thing. And I hope it actually works. I get lots of emails from people who are very, very concerned and say, how can this work? But then I think, I know, well, we're going to, of course, repeat now somehow history repeats itself, because also in the 1980s, they said, where is the dissipation? Where is whatever? And this is a dissipative, I think it has exactly the same status as the Landau formula, with one exception, of course, that here the non-equilibrium population is in K space and not in real space. So I say, yes, this is a dissipative current flowing between reservoirs. But we will argue it. I'm pretty sure people will either, just ignore it or find out that it's incredibly more efficient than what they've been doing so far, and then worry about whether it's equivalent. We calculate it in some cases, and we get the same answer as in Kubo. So I'm pretty sure that this is the correct way to do it. It's certainly incredibly more efficient, and I'm pretty sure it gives you the right answer. But again, as in the 1980s, this is not something which was settled immediately. I mean, Adi still remembers Barangay and Stone, right? Their big 50-page paper showing that it was equivalent. So there'll be discussion here, and I'm open for that discussion. But at this moment, I just wrote this down, and I say, let's calculate it. That's what I said to Paul. Paul, do it. And he came back to me an hour or so ago, and things which he had been working on for 6 months, he got the same answer. So he was kind of excited. Okay. So a cylinder. This thing here. The geometry is this thing here. Here it is. That's the geometry. Here to right.
Okay. And you look at the transmission along the distance.
Yes, absolutely. This is the geometry. And this is the band structure, but the fun thing about this Landau formula, unlike the Kubo thing, that for much of the things you don't even have to calculate anything. You can you need to see what happens, because let's just apply it. I'm just going to do it without calculating anything. So this right plot is actually a calculation of this magnetic moment. So Paul just put this in a lattice and calculate the magnetic moment of each state. But and already you see something fun. You see that the bulk states are kind of chaotic and miserable, but the surface states have a very simple magnetic moment. And we know that because what is the magnetic moment of some current which loops? It's the area times the current, right? That's the magnetic moment. Well, I know what the area is. The area is the circumference, and I know the current. That was this Fermi velocity times mu over beta. And so, and in fact, you can see something else here, because the first time in none of the papers, so there have been many, many papers on the chiral-magnetic effect. None have looked at surface effects, and the argument is like this. This is a bulk current. It's a current density. So it's proportional to the number of states in the bulk, which scales like the area, and number of states on the surface scales like the perimeter. So if your system is large enough, area wins, and so forget about surface effects. This is true. However, the magnetic moment of surface states is much higher than that of the bulk states. In fact, it's higher by precisely the same factor. And so this cancels. And so at the end of the day, bulk and surface gives comparable contributions. And in fact, let's calculate this. So I'm just trying to do this calculation, which is here. So I have to, so T, I put T equal to 1. Chi, I put Fermi velocity, area over perimeter. Number of modes, that's this proportional to perimeter. There's Fermi velocity, and you see, this is without any calculation, you immediately get the chiral magnetic effect. And then the top thing shows a numerical calculation, and it agrees brilliantly. So that's really, really fun that you can get the universal effect without doing any calculation. Just as so this is the same value as the mu driven. This is driven by magnetic field. This has the same value as the chiral magnetic effect driven by a chiral chemical potential. So that's fun. But now the bulk states. The bulk states are ugly. Yuck. And you can also see here the bulk states somehow tend to have an opposite sign of the contribution. That's depressing. What if they cancel? What if bulk and surface just cancels? Perhaps it cancels for some fundamental reason, and we're just somehow figuring this out the hard way. That's frightening. And no, they don't cancel, and there's even more to it. So first of all, they give minus 1/2. They give minus, so bulk contribution for ballistic, in the ballistic case, the bulk contribution is minus 1/2 times the surface contribution. That's one thing. Now actually this bulk contribution driven by magnetic field has been studied by other groups as well last year. There are two very, very influential papers, very insightful papers by Ma and Pezin and by Joe Moore and his group. And they call this effect, some of this is something which is known in materials. It's called magnetic gyrotropy. That there are some materials where if you apply magnetic field, the current starts to flow. Not for some topological reason, just because these materials have some local magnetic moments, and so if you apply magnetic fields, currents can flow. This is called, excuse me? This is a transport current. I'm talking about a transport current. No, please. This is nothing. This is a current which flows along a wire from one reservoir to another reservoir, so it has nothing to do with magnetization. It is a transport current, dissipative transport current.
So you have zero chemical potential difference, you put a magnetic field.
Oscillating slowly, no. Okay, hang on. So everything here is so this is non-equilibrium effect, dissipative effect. So if you apply this magnetic field and wait and come back the next day, the current will be gone. Because the things will equilibrate and then there's no current. So I'll show you a bit more the way I imagine doing this experimentally. So you need to apply an AC magnetic field. You need to oscillate. The magnetic field needs to oscillate up and down and up and down. And then you can ask what should be the frequency of this oscillation. I call it quasi-stationary because it exists, let's say, formally in the limit frequency to 0. Of course, until the frequency hits the relaxation time, the intercone scattering rate, and then it goes away. So there's a window, a plateau of frequencies, a plateau of low frequencies, where this effect is frequency independent. And then if you really send the frequency to 0, then inelastic scattering will take over and the current dies.
In the absence of any scattering, in the limit of omega going to 0, you have a time
Yes, of omega, exactly. Well, this is what I showed here. I gave you the explanation here. I've calculated here. This is simple, at least for the surface, this is simple. I cannot give you a simple explanation for the -1/2. I wish I had, but I don't. But for the surface, here's the thing. This is this one line. Number of states, so I assume that the magnetic field adiabatically, so that the non-equilibrium population is driven adiabatically, so some levels are pushed up, this creates electron excitations, some levels are pulled down, that creates hole excitations, no equilibration, and I just calculate the current. So this is the explanation in a very elementary way. For the bulk, it's more messy because you have to really calculate it. I can calculate it. I get this -1/2, but it's messy. Okay. Now so you'd say, okay, this is kind of ugly because there's this bulk effect which is somewhat trivial, it's ancient, and there's a topological effect which is the surface effect which is fun. But okay, first of all, one is 1/2 smaller. But actually, I think they respond very differently to this order. This is not something which we've calculated, but this is something, some argument very much along the same lines as Adi Stern's argument. The surface states are chiral. So if the disorder is long range and doesn't scatter all across the Brillouin zone, this order should have no effect on the surface states. Whereas the bulk states, they'll scatter. And so I'm actually predicting here that this order will help, because this order will suppress the -1/2, and so the effect will grow if you add this order. This already would be kind of striking. Adding this order and the current increases because you're suppressing the bulk contribution which had the wrong sign. And so this would be one way of okay, going to look at the sign. So the bulk and the surface contributions are distinguished by the sign, and they're distinguished that one is sensitive to disorder, the other is not. -1/2. I have one more slide and before I conclude. Let me just to show you suppose you say, well, I'm not really interested in this. I want to work on the traditional Carlo effect, the one which is driven by mu. Well, we can do a Landauer formulation there too. And then we can do for the traditional the ancient Cairo magnetic effect, the one with Landau levels, we can do something which was never done before because in the Kubo formulation it's just very painful to include boundaries. We can look at finite size effects. So this is what we did. So this is just one slide as a contribution to this ancient literature. Let's look at the original Cairo magnetic effect and look at finite size effects. So here at the right, so now you see a very different dispersion relation. This is the dispersion relation in the Landau level regime. So you can see this band of things which move like this. This is the zeroth Landau level, chiral zeroth Landau level from one cone, chiral zeroth Landau level from the other cone, and you see that they're connected by surface states. Also there, these Landau levels, they cannot just exist, forever. They have to move over to the other cone, and that's done along the surface. And now you can see what finite size effects will do. And in fact, the finite size effects will give you a Fermi energy dependence of the chiromagnetic effect. Because you see, as you move the Fermi level up or down, surface states are converted into Landau levels. And so your degeneracy of the Landau leveling is changing. And so there's a strong, pronounced Fermi energy effect of the original chiromagnetic effect, which is somehow missed if you go to the infinite system size limit. And this is the formula. Again, this is something which follows immediately from this Landau level formulation. Probably it can also be done using Kubo. I have no idea how to do it. Because I just have to count modes. But the modes, the dispersion of the modes is the same for all. I just have to find out how many modes are there. So I have to know how many of these surface states cross the Fermi level, and that's given by this number here. So you see, this is a finite size effect because this says perimeter over area. So that's different. The B-driven effect, that one without Landau levels, there the surface is as big as the bulk. Here in the original mu-driven effect, the surface is less important than the bulk, governed by this ratio perimeter over area. So you're allowed to. So for the original effect, you're allowed to ignore the surface, not for the B-driven effect. But anyway, there is this thing here. You see that this is numerics here, and the lines are just this formula here, and they fit without. No, they agree without any fit parameter. So again, I think this Landauer formulation really has some truth. I think it's really correct, and there's a pretty sizable finite size effect. And actually what's kind of interesting is that the B-driven effect, so the one without Landau levels, has pretty much no finite size effect. Here it is. So the upper thing is the B-driven effect. Hardly any finite size effect, no Fermi energy dependence. So in that sense, it's much more robust than the mu-driven effect. No finite size effect, no, well, there is ultimately a finite size effect, but you can, it's much weaker, and no Fermi energy dependence. Okay, this was just an aside, this slide, but just to show you what type of calculations we can do with very little effort. So this is now my final slide, and then we can have some questions. So this is the experiment I would like to propose. Let's say take a whole bunch of nanowires, these Weyl Semimetal tantalum arsenide nanowires, apply a magnetic field parallel to them, and oscillate this magnetic field. Now the oscillation frequency should be less than the bandwidth. It's certainly less than, let's say, this mu. So that gives you some upper range. And the oscillation frequency can be low, but shouldn't be zero because you want to prevent equilibration. So there will be some sort of plateau. And in this plateau, the induced current will be quasi-stationary, frequency independent. And yes, there is both a bulk effect and a surface effect, and they have opposite sign. Perhaps that's one way to distinguish them. And one will be suppressed by disorder and the other will not. And the surface effect is the fun one. That's the topological effect that's driven by this Berry curvature, chirality. And I would really say this is the surface effect is the Cairo anomaly without Landau levels. And now I have my final little test. So this thing without Landau levels may sound familiar, right? Quantum Hall effect without Landau levels, anyone? Haldane, 1988, Nobel Prize, perhaps winning discovery. How's this called, the quantum Hall effect without Landau levels? Has a name? No? Yes? How's it called? Yeah, no, not the anomalous Hall effect. It's called the quantum Hall effect without Landau levels is called the quantum anomalous Hall effect. So, my proposal, the chiral anomalous anomaly. Thank you.
Thanks, Carlo. We have time for a few questions. Aviv was the first one to raise his hand.
So tantalum arsenide has, so this is like a toy model. The real model, not only it has not two Weyl cones, the real systems we have so far not only have two Weyl cones, but have 8 or 24 Weyl cones, and they don't combine. Now, perhaps if you would look at if you would cut it in a proper way, I mean, I just want to have on the surface they should be separated. So perhaps it is possible, but I don't think, actually. I think you really need, no, my answer is no. You need to break time symmetry. You need to break time symmetry. You need, because I want a magnetic moment. I want something which circulates. Okay, you know, it's in the same way that the quantum Hall effect without Landau levels, it's not the quantum Hall effect without time-universal symmetry breaking. Right? The quantum Hall effect without Landau levels has some time-universal symmetry breaking by magnetization. In the same way here, this is not the Cairo anomaly without time-universal symmetry breaking. It's broken by whatever, some magnetization, but then there's no Landau level structure, no orbital effect. Thank you. Okay, so you asked this question, so let me tell you. So I struggled with a full half year to get this -1/2 because it's incredibly robust. We can do anything we want to this system. We always get -1/2. So we have numerics for a broad variety of things, all parameters. It's always -1/2. I have one analytical calculation for a toy model, where I have to put in surfaces, so I don't have much freedom to choose my model. I have to make many things just right in the toy model to make it work, and then I also get -1/2. There must be a elementary explanation why it's -1/2. I struggled for half a year. I didn't find it. Well, no, I mean, for 2 Weyl points. Probably if you have more of them. No, that's for 2. What I mean is, for example, you could say this is without Landau levels. Okay, give me Landau levels. Let's apply a strong magnetic field. Nothing changes. Nothing changes. So I'm absolutely convinced there is a fundamental reason, probably some field theory, whatever, nonlinear sigma model, which gives you -1/2. I do not have it. There's one other thing which is slightly disturbing. We have the cylinder geometry which gets -1/2. Joe Moore and his group don't work with surfaces. They just have an isotropic 3D system. They get for this gyrotropic effect -1/3. I think it's an anisotropy effect. I think there's some sort of intrinsic anisotropy in the cylinder which you do not have in 3D space. And I wish I had more control over it. I'm like confident enough to go public because we have all the numerics. So the -1/2 is certainly true. I have no doubts about that. But I'm certain that I'm missing some fundamental explanation why it should be -1/2. Excuse me. No, we don't. We do both whole and without whole. We do both calculations where we have just a real honest-to-goodness wire and where we have a wire with a hole so we can do periodic boundary conditions. We do both calculations and we get the same -1/2. So I'm convinced this is very, very robust. But I don't have... also from the analytical calculation, it just comes out after doing lots of stuff. And also there. So there's something missing there. And if somebody figures this out, he's my hero. She's my hero. Oh, the surface state, the surface effect, I presume, is independent of disorder. This -1/2 of the bulk states is certainly without disorder. I mean, if you add disorder, it can be anything. I mean, if you tell me also the bulk thing is insensitive to disorder, then I'm totally flabbergasted. I see no reason why the bulk would be... No, this is... But all the calculations, pretty much all the calculations so far have been without disorder. You know, it's pretty difficult. 3D, it's much more difficult than graphene, actually. So the theory is progressing a bit more slowly.
Maybe I'm repeating the question. If you take not a cylinder, but cylinder and...
Yes, so this is what we've done. We've done that. Yes, no, we've done. You get the same results. Yeah, so we either took a completely filled cylinder, which means that you have hard-wall boundary conditions in X and Y, or we take a geometry where we have hard-wall boundary condition in X and periodic boundary condition in Y, which really means that you have a cylinder, you have an inner and an outer surface. Inner and an outer surface. They're different because if you have an inner and outer surface, you can have a circulating current like this. But we are interested in the current along the cylinder, and we get the same results. We can do much bigger, numerically, we can do much bigger systems if we have periodic boundary condition in Y. That's why this is a convenient check, and we use that. Absolutely. Yep. Yeah, so I'm assuming that there's no... I'm assuming that the endpoints of the wire are not connected by voltage source. But you see, this is... Okay, so actually, no. So if... Suppose I've never heard of this fact that magnetic field pulls levels up and down. Then I would explain it exactly this way. I would say magnetic field generates an EMF, which accelerates the electrons, and because they spiral, they move up and down. This is, you know, the fact that a magnetic field can pull levels up and down, of course, is the electromagnetic force. I mean, it's ultimate. Once you give me a Cairo Landau level, the whole theory is just classical electromagnetism. So it's not some new bizarre effect. The bizarre effect is that you have stuff which moves only in one direction. But if you give me that, then yes, the reason why a magnetic field generates a population imbalance is just electromotive force.
One way symmetry of the crystal and also close the structure is the photogalvanic effect. In the photogalvanic effect, I'm sure you're familiar with implied light or electromagnetic wave with particular polarization, either linear or circular, and you observe the current in the other direction. There is a tensor that connects the electric field and this current. So will there be any anomalous effect with or without?
I'm sure there will. In fact, I do know in the literature optical signature, theoretical proposals, perhaps even experiment for optical signatures of the chiral-magnetic effect. The literature is exploding, and I remember distinctly that there was one contribution along these lines. It's not something which I've explored here.
Maybe one last question. So I would actually have one. Carlo?
Yes, tell me.
So, so here you basically have a system which is periodically driven, and you say, on one hand, I don't want it to equilibrate. On the other hand, you want a steady state. So, is it equilibrium or non-equilibrium?
No. Okay. So if in the Kubo formula, here's how it happens. Here's how it works in the Kubo formula. So you would typically say J of omega is some response coefficient proportion, and then multiplied by omega, and the response coefficient goes like 1 over omega. So the quasi-stationarity comes from the fact that the response coefficient is 1 over omega. And this basically is a consequence of the Cairo magnetic effect. If omega is very small, then this EMF has a very long time to make the particles move around. So in the linear response calculation, the cancellation of omegas is very explicit because you start out with something which is multiplied by omega, and you only get the quasi-stationarity because the response coefficient is 1 over omega. Here, you know, like nothing like that ever happens. But it's the same thing.